we can even start. So please.
Easy. Yeah. Hello, everyone. So, yeah. Thank you. Hello, everyone. My name is Diego. I'm a PhD student in the University of Wisconsin-Madison. My supervisor is George Craciun, and this presentation is about two papers mainly. One that it's already in archive with George Craciun and Polly Yu, and I'm still writing the second one, which should be up in archive by the end of this semester, which is also with Yashin Jin. So I gave a talk already about this a year ago, right? So I'm going to remind everybody of the things I talked about in the last talk, and in case you haven't seen it, present it for the first time, and then I'm going to go and present the newer results that are going to be published soon. Okay. So the title of the talk is Extending Mass Action Theory, Causality and Permanence in Generalized Lotka-Volterra Systems, and we're going to understand all of these terms. But to start, we should consider the question carries. So let's consider like the possible dynamics of different reaction networks. These are three examples. A priori, it's hard to tell what the dynamics are going to be because we just have a collection of differential equations. Very hard to determine what can happen with a collection of differential equations of this type. Famously, Hilbert's 16th theorem tells us that we still don't know even the very basics in 2 dimensions. But in these specific cases, we do happen to have very nice dynamics. The first one has a unique globally attractive equilibrium. The second one has bistability, and the third one has a limit cycle. So we're going to be interested in seeing why systems of this type have very nice dynamics. In this case, they can be explained by a number of theorems for mass action systems. The first one being Horn-Jackson theorem, the efficiency zero theorem, more generally the global attractor conjecture, persistent conjecture, and permanence conjecture. So, also some conjectures. And we're going to see how more about this nice little theory compared to generalized Lotka-Volterra systems. So generalized Lotka-Volterra systems are coming from what's called the Lotka-Volterra system. This is the one here. This is used not in biochemistry, but in population dynamics. So here, these three reactions represent a predator-prey model. For example, the predator here is Y and the prey is X. We can think of foxes and rabbits. I like that. So you see, foxes, they eat rabbits. So when a fox eats a rabbit, you lose the rabbit and you get a fox. So you have two foxes. Foxes also just die on their own. And rabbits, everybody knows like rabbits reproduce very, very fast. So one rabbit will give you two rabbits, just like that. And we can represent these equations, like this model with this set of differential equations. The important thing here is that all of the interactions, that started with dx1 dt can be factored out by x1, and in the dx2 dt can be factored out by x2. And this has a little bit of a nicer algebraic structure, we might say. And we're going to generalize this structure to the generalized Lotka-Volterra systems. We're going to worry about equations that are like the xi dt equals xi times some function. We'll determine these functions and how they look like later. So for these types of systems, my question is, can we also have a nice theory? So now it's not for a biochemical application, but for population dynamics or maybe epidemiology application.
Excuse me, Diego. Excuse me. Will you assume that the functions f are linear?
No. The functions f can actually be very, very nasty. I'm going to have my only assumption is that you can separate them in monomials. Yes. And each monomial can have, so George calls these power-like functions. So they can even have negative powers, so we can have fractions.
Okay, well,
it's going to be.
It's not so important, but these systems of this form are also called Kolmogorov systems when X1, X2 can be pulled out. Okay, not important. Thank you.
Yes, yeah, many names, but I'll give like a specific definition here. So well, the point here is we a priori don't have any corresponding theorems that tells us about the structures. Like there are a number of theorems of how generalized Lotka-Volterra systems might behave, but they don't have analogous to the ones we have in mass action systems, which are very nice taken from the graph structure. So first we need to remind ourselves what are these classical mass action theorems I've been talking about. So I'll take the Lotka-Volterra example for to define what a reaction network is classically. So here, if we interpret this as a classical reaction network, then we'll have species, complexes, and reactions. Species are going to be X and Y, Fox and Ryan. Complexes are all the possible combinations. Reactions are all the possible reactions that can go through these combinations. And we'll interpret this as a graph embedded into R2. So I'm going to embed the complexes as vertices with specific coordinates in R2, and the reactions are now going to become reaction vectors. And this is for simplicity, it's a notational choice. So mass action kinetics, well, if we take one reaction, what's going to and how we're going to define it is that the reaction will be proportional to amount of X here and amount of Y. So if we consider like a fox eating a rabbit, this will happen depend if there's more foxes will eat more rabbits, and if there's more rabbits, the foxes have more rabbits to eat. So it's going to be proportional to both the amount of foxes and the amount of rabbits. We represent this by saying that our vector will change with respect to x1 and x2. And now in this vector form, I'm going to say that we're removing we're removing rabbits and adding foxes. So whenever this reaction happens, we get -1 for the number of representing that we lose a rabbit, and +1 representing that we gain a fox. This is pretty standard. You can, if you have multiple reactions, you can just add them. And now we have a system that has this nice little form. And we generalize these to what we call mass action kinetic systems or other names, but basically they will all look on this like this form. The XT is the sum of this I, j in E, I'm represented as the edges in our graph. Some reaction rate constants, kappa, ij, and then x to the power of yi, where yi is the first complex, and yj is the complex that comes out of the reaction. And this structure, we're also going to use the multi-index notation for the powers. Okay. So we have very nice theorems coming from this. The first one that I'll mention is Horn-Jackson theorem. That tells assume we have a state that is nice, which is going to be called complex balanced. I'll explain that in a moment. But the important part is that if you have one of these nice ones, all of them are going to be nice. Then there's also a Lyapunov function, which allows us to say something stronger, which is that all the states are going to be locally asymptotically stable. Also, I'm not saying here, but also they're not going to have any cyclic trajectories and a number of other properties, all coming from this Lyapunov function. So basically, we can already have some structure if we know that the state is sufficiently nice, being complex balanced. So why is complex balanced? It's just a formula we can calculate, and basically it just means we take the flow. We can represent this as a flow in equals a flow out. These two parts of the equation are just a way of representing the given state flow in and flow out. So it's similar to like Kirchhoff's law and all of these other laws where we want to balance things. Now we also need a couple of other things to explain the other theorems. We say a graph is weakly reversible if every edge is part of an oriented cycle, and we are dealing right now with graphs embedded into R2 or Rn. So this is going to be a property that our reaction networks can have. So as an example, this is weakly reversible because it's all cycles. While the Lotka-Volterra equation we were seeing before is not weakly reversible. There's no cycles there. And we also have the efficiency. No, I didn't write it here, but it's just a formula that it's similar to a topological invariant. M is just going to be the number of vertices. L is going to be a number of connected components. And S is going to be the dimension spanned by these vectors. So in the first one, the efficiency is 1 because we have 5 vertices minus 2 connected components, and this is a two-dimensional. The graph we can see as being embedded into two-dimensional space. So the stoichiometric dimension we call is going to be 2. So efficiency is going to be 1. Similarly, in this Lotka-Volterra example, we also calculate is 1. Please use a number that is always bigger or equal to 0, and it depends on the embedding and on the graph. And an important thing is complex balance. This weird property will imply that our graph needs to be weakly reversible. So we focus on weakly reversibility. And now we have the efficiency zero theorem, very nice, that tells us that complex balance for all choices of the constants is equivalent to being weakly reversible efficiency. So this is great because it means we can focus only about the structure of the embedded graph, and that will give us something about the dynamics of the system. And so this we call the efficiency zero theorem by Farmer, Horn, Jackson. So we start with assuming that a graph has this property of the efficiency 0. Then we can answer all possible questions we want about the dynamics. So, like if it's weakly reversible, does the system meet a positive equilibrium? Yes, always. And it's going to be this special type of equilibrium. Is it unique? Yes, as long as we restrict ourselves to stoichiometric compatibility classes. Is it stable? Yes, it's going to be locally asymptotically stable. And there's not going to be any periodic or cyclic solutions. If it's not weakly reversible, then there's no positive equilibrium, and there's also no positive periodic solutions. So we can fully, in a way, characterize the dynamics of these types of systems. Very powerful, only about the structure. And there's also a couple of conjectures. The global attractor conjecture says that actually it's going to be globally attractive, not just locally attractive. That is, from any starting position, all trajectories will go to a steady state. The persistence conjecture, which says that any weakly reversible mass action system, so now we forget about the efficiency, only the condition of weak reversibility, will have this property of persistence, which means the trajectories will not go to the boundary. So basically means in a if it's weakly reversible, no species will go down to 0. And permanence conjecture also, only the condition of weakly reversibility gives permanence. There exists a globally attractive compact set such that all trajectories go to the compact set. So in our first, when we were first showing the possible dynamics, all of them were weakly reversible and all of them were permanent, all of the trajectories went to a compact set. But my focus is not on the mass action theorems. It's on trying to bring these theorems to the generalized Lotka-Volterra systems. So first, let's discuss see some examples of generalized Lotka-Volterra system, see what properties they have. So this is a very basic generalized Lotka-Volterra. In this case, the Fs are linear. They don't need to be, but in this case they are. And because it's linear, we can separate how we represent these equations here with how the matrices that index all of the interactions between xi and xj behave. So if we have a matrix, if it looks like the end, we have a matrix where all of the off-diagonal entries are non-negative, then we're going to say that this is representing a cooperative system. So it's a mutualism in like population dynamics. Well, if they're negative, it's going to be competition. So now this is not predator-prey, it's either all mutualistic or all competitive about the same resources. And the interesting thing is that Smell and Hirsch proved that there's basically any dynamics can be found if we just look at competitive with linear term generalized Lotka-Volterra systems. So living cycles are possible. Anything is possible for 5 or more species. And here are a couple of examples. So this first one, it stabilizes these 3 species. The second one, they stabilize in a positive equilibrium instead of a boundary equilibrium. This one, it's just cyclic behavior. And finally, this one is chaotic behavior with 4 species. This is a case that was proven to have chaotic behavior. So a priori, just with these very simple limitations of generalized Lotka-Volterra systems, many things can happen. So we need to be careful in how to define our theory, because we want very specific dynamics, very nice dynamics to happen. So we'll need a way to identify when these nice dynamics happen. Okay, this is a very explicit example. So we can ask, okay, can the system have a positive equilibrium? Is it unique? Is it stable? Are the cyclic solutions? The same questions we were asking before. We can interpret this system in many ways as a mass action system. This is one example where I interpreted the components of from the ODE as a mass action system. And as we can see in this example, we don't satisfy what we want because the efficiency is 1. It's not weakly reversible. So there's no complex balance equilibrium or the efficiency 0 theory. It's very hard with looking at this as a mass action system to use our theory to determine what happens. So we want to be able to deal with a case like this one, which is known in the classical theory of generalized Lotka-Volterra systems to actually have an answer to all of these questions. So we want to be able to get this from a structure of a graph. Is there any way to deal with this case, similarly with the efficiency theory? So now the goal here is to develop a theory that is very similar to mass action, but applied to generalized Lotka-Volterra systems. So for this, we go back to the embedded graph that we were thinking. So before with the reaction networks, we had an embedded graph, and then from that graph, we were getting a differential equation. If we want to apply it, we might need to try to find a graph that gives us the same differential equation and try to see if we can apply any of the results. So this worked well for mass action kinetics, and we have the theory there. But now, for generalized Lotka-Volterra systems, because this was not working, we propose a different way of getting these differential equations. So we'll start with the same embedded graph, and we'll generate a different differential equation where f is the same. So we're going to generate something that looks more like the structure we had for generalized Lotka-Volterra systems. We already started with multiplying this diagonal x, just means in dxi dt, we're going to multiply xi times fi. So what do I mean by this? Before we were generating from a graph the system on the left, now we're going to generate for a graph the system on the right. And it looks already like it comes with the structure of what we want for generalized Lotka-Volterra systems. So let's do an example to understand what's going on. In this example, we want this system. I already factor out x1 and x2, so it's easier to see how to generate it. Before, when we wanted to realize this from a graph with mass action, this is a graph we found, but it wasn't very nice. But now, if we look at what would f1 and f2 be, these are very simple functions right now. They're linear. So we can find a generalized Lotka-Volterra, a different graph that through this different process, we get the ODE we want. So this graph in blue here on the right would be a graph that gives me, through mass action, F1 and F2. And then we'll say that as a generalized Lotka-Volterra system, the graph gives me the ODE I had in the beginning. Okay? So I'm generating a different ODE from a graph. And this graph now is going to be much nicer. So both of these graphs are representing the same ODE, just the first one is represented as a mass action realization, and the second graph is representing as a generalized Lotka-Volterra realization. And now from these two graphs, what's the advantage? Well, the first one is not weakly reversible, while the second one is. And the first one has efficiency 1, while the second one has efficiency 0. So the first one cannot have complex balance equilibriums, while the second one does, and for all reaction rate constants will have a complex balance equilibrium. Okay? In this specific example with 1, 1, 1, 1, the complex balance equilibrium happens to be 2, 1. Okay? So if we would say, oh, we know everything, if we had the deficiency 0 theorem for the generalized Lotka-Volterra realization. But we only right now have the efficiency 0 theorem for the mass action realization of the graph. So that's the situation. We need to build a new theory for the generalized Lotka-Volterra realization. So we'll do that. We can ask, can we build an analogous to these theorems? The surprising thing is we can. The first paper talks about that. We do have an analogous result to Horn-Jackson theorem and to efficiency 0 theorem, and even to a global attractor conjecture, which is surprising because the global attractor conjecture is not fully resolved in the mass action system, in the mass action setting. But now that we jumped to a different setting, generalized Lotka-Volterra, we can actually prove that it's going to be globally stable. So let's see those results. Basically, comparing left and right, before we had the Horn-Jackson theorem, which says for complex balance state states, these nice state states, we have the specific Lyapunov function, and we get locally stable state states. Now we have a new theorem, which says that under complex balance state, then and we're going to define what complex balance means here. Then opposite states are going to be complex balance. There's a Lyapunov function, and every positive state is globally stable, not just locally stable. So as you can see, it's similar, but the Lyapunov function we get is slightly different. And it's very curious that we can actually extend this theorem from mass action systems to this different setting and even get a stronger result. So also we'll be able to extend the efficiency 0 theorem, which says that weakly reversible efficiency 0 was equivalent to being complex balance for all reaction rates. Now will be equivalent to being complex balance as a generalized Lotka-Volterra system for all reaction rates. And complex balance here will basically mean the same, because we can consider complex balance as a property on the F1 through Fn functions. So we can look at those functions, or on the graph itself. We can look at the graph itself and see that it's going to be complex balance. It doesn't depend that much in which type of realization we are applying to the graph. So the bottom line will be that if we have a graph generalized dynamical system as a generalized Lotka-Volterra realization that has efficiency 0, we have the answers to everything we had before. If it's weakly reversible, we'll have a positive equilibrium. It will be unique. It will be globally stable, and there will be no cyclic solutions. If it's not weakly reversible, then we will not have a positive equilibrium, and there will be no positive periodic solutions. So this is a big result. We can apply it to some simple cases to understand what happens and how does this work. So we had this example before, and again, this graph here generates as a generalized Lotka-Volterra realization the ODE on the left. So if we were to apply and we were to generate the mass action system from this graph, it would be a different system, but we're generating the generalized Lotka-Volterra system. Now, because the graph is weakly reversible and the efficiency is 0, it has a globally attractive positive state. And indeed it does. We can see here, I just ran this in a computer program to see all of the trajectories, and indeed the point 2, 1, it's a globally attractive positive state. So more generally, we can apply to many cases. In this example, we'll do cooperative generalized Lotka-Volterra systems. So again, why is this cooperative generalized Lotka-Volterra? I'm taking these simple ODEs, which have xi times a linear factor, so these are quadratic right-hand sides, and we can order them through a matrix, and I'm saying that the matrix is going to be positive in the off diagonal. So this is representing a system with n species where it's all mutualistic between them. Then we require a condition, which is if there exists some D's such that we have an inequality, then the system is going to be given by a deficiency 0 graph, so we have all of the information we want. Now, this theorem right here, it's a theorem known for a long time, but it's interesting that we can fully recover this result for this type of systems with our theory. So this is like the first check. Our theory recovers some of the structural results already known for generalized Lotka-Volterra systems. But we can extend it. Well, the previous theory could not be properly extended.
Excuse me, Diego.
For high.
Excuse me. I wonder what happens in the very classical Lotka-Volterra.
In the very, very classical Lotka-Volterra?
Yes.
So what happens in that one?
X minus xy and xy minus y. These are the right-hand sides.
Yeah, so in that one, the graph we get is neither deficiency 0 nor weakly reversible. I will say that I do believe we can do something, but it will be the scope of future work. I think we can actually explain why it's a center. It will come because it has a structure. It's a complicated technical thing that I can tell later, but it will not come directly from the deficiency 0 theory or weakly reversible.
Yeah. Okay, thank you.
Yeah. Okay, so the point is, right now here, this shown here was already known, but we can use this theory very easily to harder stuff. So, for example, I can have higher order interactions. Why is this? Well, when scientists and ecologists model Lotka-Volterra, generalized Lotka-Volterra type of interactions in mutualistic systems in the wild, they're using an approximation of, they don't want to do all of the terms of the Taylor expansion. So we can think about what if we apply more terms of the Taylor expansion of trying to model these sort of interactions, and then we can have higher and higher orders. So in this case, we have a cubic system where we're applying, when we had the FIs are now going to be quadratic. So these sign conditions don't matter too much. It just means that it's going to be sort of like the equivalent of a mutualistic system, but we're now exploring more, use more terms to better approximate what's going on in real life. So in the simplest case would be 2 dimensions. We have something of this sort, and under the proper sign conditions, what we get is that we can generate this system from this graph right here on the right, which is a square. So you see this square graph, it's giving us this ODE, which is cubic. And because this is, well, it's clearly weakly reversible, we can use our we can use our new theory to find conditions for global state. Sorry, I said the efficiency is 0, 0. Not quite the efficiency 0, but we can use a new theory of complex balance states to find when this is globally stable. And actually, what happens in this case is if we are smart about trying to find when the system is complex balanced, we can prove that for any choices of rate constants here under the correct sign conditions, this is going to be globally stable. So it's very strong. This it's not always it's going to be for all when it's not efficiency 0, but I'm going to explain the details here, but you can do some algebraic computations to try to find when it's complex balanced. And the theorem is that if it's complex balanced, then it's globally stable.
Excuse me, Diego. Here, R1 and R2 should be positive or not negative, right?
Yeah, so here, R1 and R2 should be, I didn't put the sign conditions, but R1 and R2 should be positive.
Okay, so then returning to the classical Lotka-Volterra, you have there -1 on the second component of the right-hand side. I don't know how to draw a graph to it. Okay, if you take the classical Lotka-Volterra, the second equation looks like y times x minus 1. And I don't know what to do with -1.
Yeah, I could write it here. So basically,
so you always assume that these are kinetic form, these linear or nonlinear factors. You always assume.
No, so basically, for this specific theory that I'm building here for these results, I do not need as strict conditions as for as the ones we have for mass action systems. So actually, I can have things that, can you see this? I can have something that goes from x to like -y. Okay. And the reason being that's why I want to define everything in terms of the graph, because in the graph,
yes. But in your example, again, you take positive B1 and positive B2 in the example.
Oh yeah, so
maybe
there should be negative. So there should be negative under here. Basically, the sign conditions here are like I apologize. I maybe should have included the sign conditions. So these ones are positive.
Yes.
A11 is negative. A22 is negative. Then this one is positive. This one is positive, and this one is negative, and this one is negative. These are there are a number of papers that use even this specific system, and these are the sign conditions that make sense for the system to be cooperative.
Okay, thank you.
Yeah, the sign conditions just come from wanting the system to be cooperative. Okay. Oh, need to clear everything. All right. Well, all right, so this is the first part. And basically this theory with the higher interactions, I'm not showing it here, but we can extend it to higher dimensions, because the proof of the global stability is for any dimensions. So I don't need to restrict myself to 2 dimensions. And also,
Diego,
here.
Diego, may I ask something here? Here for this reversible square, the deficiency is 1. Isn't that a problem for you?
Yes. The efficiency 1 means that I need to focus just on the complex balance states. In practice, it's not a problem because we can do, like, even a priori, we can just also do all of the techniques of the disguised toric locus. Because the theorem proven here, is the Horn-Jackson theorem equivalent, right?
Okay.
So with the Horn-Jackson equivalent, it's as long as I can have complex balance, I'm going to have global stability. And the theory, and like complex balance, as defined here, it's a property of the graph. So, for example, if we know that this graph right here the disguised storage locus, which tells me when it's going to be the system equivalent to complex balance, also applies to this setting.
Mm-hmm. Okay, thanks.
Yeah. So if we can, basically another nice thing about this theory is that a lot of complicated things, I don't need to build them from scratch, because all of the algebraic aspects of the mass action systems can be translated very nicely into this setting. So if there's complicated theorems about how to identify when something is complex balance, like this guy's storage locus, this is one of those things, we can apply it in this setting. Anyways, I'll move now to the latest work, which has time-dependent parameters. So I think this is another very interesting aspect. So we can extend the results of allowing time-dependent constants. So, well, not constants, parameters. So we're going to define a variable K generalized Lotka-Volterra system in this setting. So this is the same we were defining before, but now the kappas allow them to be time-dependent. And the only condition is that they need to be uniformly bounded away from 0 and away from infinity. So they need to have the same sign the whole time. So if we have that, then we have two very nice theorems, which is, and the second one is the most important, which is if the graph is weakly reversible, then the system is going to be permanent. So there is a compact set where all trajectories go towards that compact set, and this is even if we're allowing the rate parameters to be time dependent. So this is very powerful. We have not proven fully the analogous in the mass action system case. There's some specific conditions where we have proven it, but here it's very straightforward to prove it for any dimension. In any case. So now, coming back to this, we can also prove the analogous of the persistence conjecture and the permanence conjecture, this very hard setting of allowing time-dependent parameters. So we have this equation. Now, here I put the sign conditions. Yeah. Sorry. So here we have the sign conditions of the square, the Hadronic interaction. Square is going to be here, and we want all of the Ri, Aij's, and Bi's to be one away from 0 and infinity. And then this system is weakly reversible, so it is permanent. This is very, very powerful, because now we can apply to many realistic systems. Like I am imposing very little conditions on these parameters to be time dependent. They could be any number of functions as long as they satisfy these conditions. So, for example, to apply it in population dynamics, I might say, well, I can model it like this, and before I didn't like the constant parameters because I know throughout the cycle of the year, some of the parameters fluctuate. But I also know that if there's a mutualistic interaction, it's not going to stop being mutualistic in winter. They come from many times mutualistic interactions and mutualistic throughout the year. So the signs of these parameters is going to usually be the same throughout the year, but it might fluctuate. And all of those conditions will satisfy the theorems, and now I don't need to even worry about specifically what functions those parameters are. I can just know the system will be permanent, which is very important to know. So this, I think, I want to explore this more because this, I think, might have the most application to real life ecologists working on all this. And it's a very nice theorem just from the mathematical point of view that we can just prove that it's going to be permanent. Yeah. All right. So that's mainly it. And I have some extra slides for proof ideas. So I can very quickly you say the very basic proof idea and maybe not go into the harder details, but the idea is that why everything works is we have a change of variables. So we have this ODE system. And basically, we apply a logarithmic change of variables. And after applying a logarithmic change of variables, the system looks like this one below. And it's sort of like a mass action system, the one below. But instead of having the terms to be x to the power y, it's just going to be an exponential of an inner product. So this right here, it's a lot more, it has a lot more linear structure integrated into it. And more importantly, this dynamical system below defined over Rn. So it's much easier to define other things that complicate our lives in mass action system where we need to restrict to the positive orthants. In this case, we can actually always work in the full space for the dynamical system. So that takes away a lot of preoccupations, and it's the reason why I can allow many other things with no problems. Yeah, so we're going from positive coordinates to the whole system, thanks to the logarithm. And basically, here, the Lyapunov function that makes everything work is just the simplest Lyapunov function. It's just the norm. Like the distance to the complex one state. So it will look just like spheres around the complex one state. And a Lyapunov function works like saying that the trajectory will always decrease through the Lyapunov function. So if you haven't seen Lyapunov function before, they basically are like a potential energy, and you're proving that your OE will always decrease in find the minimum of the action, and you'll find the minimum of the action. And basically, you can very simply prove that the trajectory always, the radius of the trajectory is always going inside these spheres around the state. I think that's the main thing. And to prove permanence and stuff, basically just modify the Lyapunov function slightly, but it's so nice that it's very easy to do. Okay, that's the main talk. Any questions? Jump around. I don't need these details.
So, Diego, can I just ask a question? So you said modify the Lyapunov function slightly. So do you use some kind of differential inclusion to achieve that? Like log of x?
Yeah.